This is flow over the cylinder. So this is the streamline. This is the equipotential line. This is flow through duct. So this is the streamline. So this is the equipotential line for that. So for any object, we can draw this flow net. From this, we can find what is the velocity. That is, if you know stream function or velocity function, for example, if you know the velocity potential phi, if you want to find x and y velocity, then simply you have to differentiate this in x direction. That will give you the x velocity. Then if you want to find y velocity, simply you differentiate with respect to y, you will get y velocity. So from this velocity potential, we can find u and v velocity. Once you know the velocity, you can find the pressure, then Cp, then Cl, Cd, whatever you want, you can find it. That's the idea. Using that only, we found, we derived that source panel, vortex panel, everywhere we found from phi to velocity, then velocity to Cp, etc. and all we found it. Okay. So once you know the phi, you can find x and y velocity, dou phi by dou x, dou phi by dou y. So this I can write it as phi x, another symbol. Instead of dou phi by dou x, I can write phi x. This I can write phi y. Similarly, if it is dou u by dou x, then this should be dou by dou x of u. U is dou phi by dou x. And this can be written as dou squared phi by dou x squared, that we can mention as phi xx. Okay. So dou u by dou x, I can write it as phi xx. Similarly, dou v by dou y, I can write it as phi yy. Then dou u by dou y, if you want to mention, then I can write it this as dou xy. Okay. So this is for incompressible. Okay, 2D steady irrotational incompressible isentropic flow. That's what we assumed in AD1. So we are starting with the continuity equation, dou rho by dou t plus del dot rho v is equal to 0, general continuity equation. And for the steady flow, property will not vary with the time, dou rho by dou t. So this is 0, and this is the remaining term. If you take 2D, if it is 3D, there will be dou by dou z term also, but this is 2D. Okay, this alone I have written here, dou u by dou x plus dou u by dou y. So here density is constant because incompressible. So if you take it outside, then it can get cancelled. That is, if you take it to right hand side, it will get cancelled. So this will be your final continuity equation for 2D. Okay, this is very familiar to you, continuity equation in 2D. And instead of dou u by dou x, I can write phi xx. U means dou phi by dou x. So if you, then dou u by dou x means dou square phi by dou x square, that is phi xx. So instead of this, I can write phi xx phi yy. This is the Laplace equation. This is the very basic. From this, you will find phi, then velocity, Cp, Cl, everything like we did it in the source panel, vortex panel. This is the first one that you studied in fluid dynamics itself. Just from the continuity, we are writing the phi equation. Similar way, we are going to write it for compressible flow. Okay, same assumption, 2D, steady, but here it is compressible. So same continuity. So this term is cancelled because the flow is steady, and here density is not constant. So you cannot simply take it and cancel it. So both are variable. So if you want to differentiate, you have to do for differentiation of UV formula. Okay, so if you differentiate this first term, you will get this one. Okay, so rho u dou u by dou x plus u dou rho by dou x. Then second also both are variable. If you differentiate, you will get this one. And now I can convert all possible term to the phi. So dou u by dou x is phi xx, u is phi x, dou v by dou y is phi yy, v is phi y, and remaining term, okay, density, just same term I am taking it. Only this term I want to convert now. So this is dou phi by phi xx, phi x, phi yy, phi y. Only these two terms I have to convert. So to convert that, so I am taking this Euler equation, dp is equal to minus rho v dv, and velocity, so I am taking in both direction, u and v. Okay, so u is v cos theta, V is V sin theta, two components I am splitting, resultant V. So V square is equal to U square plus V square. So this V dV, I can write it as T V square by 2, because if you differentiate V square by 2, you will get 2V dV by 2, 2 get cancelled, you will get V dV. Okay, so instead of this V dV, I am writing d of V square by 2, and instead of this V, I am taking two components, U square plus V square. Then again this one, it can be written in the same way, U du plus something understood. Okay, U du plus V du. So this dP formula I am writing like this. So instead of the resultant velocity, I am taking its components. So I don't want this dP also, because what I need is dou rho by dou x. I don't want this dP. I need d rho. So I know the relation between dP and d rho. So a square is equal to dou p by dou rho, dP d rho, anything you take it. This is from the speed of sound. Okay, a square is equal to dP by d rho. So I can write dP is equal to a square d rho. Okay, instead of dP, I am writing a square d rho, and a square I am taking to the right hand side. So it will be d rho is equal to minus rho by a square. This term I am getting. Okay, so I don't want dP. I am converting that into d rho. Now I can write this in both direction. That is dou rho by dou x, the same equation. I am writing in both x and y direction, dou rho by dou x and dou rho by dou y. Okay, so u I can write it as phi x. This is phi xx, phi y, phi yy. Similarly, dou rho by dou y I can write it. Now these two I can substitute here. Okay, so this term, and this one is here, this one is here. Like that I am substituting. Then rearrange. This will be the final equation. Two forms are there. Any form you can take it. Velocity potential equation for compressible flow. So this is the non-linear partial differential equation. Now we are going to convert this into linear equation in two methods. So one is the linearized theory method, another one is the method of characteristics method. So first we will see this linearized theory method. So in this derivation, so this is the first concept. So assume the free stream velocity v infinity. You know, here it will be just horizontal direction. There is no vertical direction. This is the free stream flow. And here we have the object. So we have the aerofoil. So this object creates some disturbance in this region. So it changes the velocity. You know, above it will be accelerated. Below the wing it will be decelerated, right? So this object creates some disturbance. So there are some incremental velocity or decremental velocity added to this v infinity. Okay. So here, so because of this disturbance, v infinity is changed to v. So this v, how I can write it? It means, so first here I will tell you. So this free stream, it has only the u velocity. V is 0. Okay. Only x direction is there. Vertical direction is 0. So u is equal to v infinity we have taken. But here it is little bit tilted upward. So this v, how I am writing is v infinity plus u cap. This is horizontal component, and vertical component v cap. So this v cap, u cap is the perturbation velocity or disturbance velocity. So because of this body, so it creates some disturbance in both direction, x and y direction. So x direction disturbances is u cap, y direction disturbances is v cap. Okay, so these two components are adding to this free stream v infinity. Okay, so because of this body, it creates disturbance velocity u cap v cap that is adding to this v infinity. So in above it is accelerated, so then this should be the positive sign. In below, if you are taking, it will be decelerated, that means this will be the negative sign. Okay, incremental, above means incremental, below means decremental, this u cap. Is that where we are calling this u cap v cap as disturbance velocity or perturbation velocity? Okay, I am assuming this object is very thin, like a flat plate. Okay, and angle of attack is very small. This disturbance velocity is very small. That is my assumption I am taking. Okay, so thin object, small angle of attack. So this creates very small disturbance to the flow field. So there is a very small u and v, u cap and v cap velocity. That is the assumption. Using this, we are going to simplify the nonlinear form. So this is the nonlinear velocity potential equation we derived now. So you can see here the same equation. Okay, it is here. I converted phi to u. Okay, phi x to u, phi y to v. Either I converted because instead of u, I am going to substitute this. Instead of v, I am going to substitute this. So instead of phi, I have taken u everywhere so that I can simplify this equation. So this is in nonlinear form. This is another form I have written in the velocity term. Now, so I know u is equal to phi x, v is equal to phi y. In similar way, I am writing u cap as phi cap x, v cap as phi cap y, and this also I am going to convert it. Phi xx, I can write it as dou u by dou x, and instead of this u, I am going to write v infinity u cap, and this v infinity is constant. Okay, free stream velocity will not vary, only this u cap will vary at different location. So this is constant, so differentiation of constant will be 0. You will get only dou u cap by dou x, that will be phi cap xx. Okay, similarly phi yy, it can be written as dou v by dou y. Instead of v, I can write v cap, and this is phi cap yy. So everything I am going to substitute now here in this equation. So the same equation I have written here. So instead of this, I have taken phi cap xx, instead of this phi cap yy, and instead of u, it is v infinity u cap, and this is phi cap. Instead of v, it is v cap. Instead of u, again it is v infinity u cap. Here it is v cap. And everywhere there will be a cap. So normal equation in terms of this perturbation velocity I converted. Okay, now further I am going to simplify this because this is also a nonlinear form. So same equation I written. Okay, substituted. Same equation I written here. So I am taking this v infinity outside from everywhere. So outside I will get this v infinity square by a square, which is m infinity square, and inside I have these ratios. And already I assume I am using the thin body with a small angle of attack. That means this perturbation is very small. Okay, so u cap v cap is very small compared to v infinity. Then if you take this ratio u cap by v infinity, it will be very less. So I am going to cancel this, neglect this u cap by v infinity terms everywhere. This is the assumption. Okay, so the disturbance velocity is very small because of thin body and small angle of attack. If this itself small, then u cap by v infinity will be very small. So I am neglecting that from the equation. So remaining you will get phi cap xx, phi cap yy minus m infinity square this term, and this term will be there 1 into phi cap xx. Remaining will be cancelled. Okay, so phi cap xx, phi cap yy minus m square into phi cap x. Only this term will be there in this above equation. If you apply this, then they are rearranging it. Phi cap xx, if you take common, you will get 1 minus m infinity square plus phi cap yy. This is the final velocity potential equation in the linear form. So this equation is valid for only small perturbation, that is thin body with a small angle of attack. It is not valid for large perturbation induced by the thick bodies and large angle of attack. And it is valid for only high subsonic flow 0.4 to 0.8, and for the supersonic 1.2 to 5. It is very, and it is not valid for transonic and hypersonic. Okay, don't forget. This you have to memorize. Why? Because that we are going to derive the CP. From that we will draw this graph. I will explain now itself. So we will derive these equations in the CP compressible, incompressible and all. After that, if you draw the curve, it goes like this. Okay, this is a CP curve for different Mach number. This is sonic, and from supersonic again it will go like this. So up to this it is incompressible. So it is not effective. Only this equation shows the effective value from this Mach number 0.4. Actually, few books they mention 0.3 also, but many of the books they mention from 0.4 it may give you the proper value. Okay, from 0.4 to 0.8 you can get the proper value if you use this formula. After that it will goes to infinity. For example, if you substitute 1 here, Mach number 1, it will be 0, right, bottom portion. So anything by 0 will be infinity, right? So this line goes to infinity. So you won't get results within this region. Similarly here also, this is for subsonic, this is for complete subsonic and supersonic. So it is effective only from 0.4 to 0.8, and in this region it will give you the infinity value. Similarly here also up to 1.2 it will give you the infinity value, and it is effective from 1.2 to 5. Up to that it will show some changes. After 5 it will be like a straight line. It is won't effective. Okay, so low subsonic also it won't show any variation, so it is not effective. Only 0.4 to 0.8 this linearized method is effective. Then from 1.2 to 5 it is effective. In the transonic region, low subsonic region, hypersonic region, it is not valid. Is that clear? So we are going to derive the CP equation for the linearized theory. So this is the final form. So I am starting with the general formula. Cp is equal to P minus P infinity by Q infinity. And instead of this Q infinity, I can write half rho V square. And I know how to convert this half rho V square into gamma P M square that we discussed in nozzle expansion and all. Simply in this equation, we have to include this gamma P by gamma P, that's it. In this half rho V square, include gamma P by gamma P. Now this gamma P by rho is A square. So this term is M square. So remaining will be gamma P M square divided by 2. Okay. So this we discussed already, how to convert half rho V square into gamma Pm. Now substitute this term here and rearrange. This will be your final Cp formula in terms of pressure and Mach number. Don't want this P term. Finally, I need this U term. So to relate that, first I am relating P with P to the temperature, that is using isentropic relation. Then temperature to the velocity using energy equation. Okay, so I want to convert this pressure into velocity. For that, first they are taking pressure to temperature, then temperature to velocity. Okay, so this is isentropic relation. This is normal energy equation. This is also up to this, it is normal steps. This is the normal energy equation. We know H is equal to CPT, and Cp is gamma R divided by gamma minus 1. That's what they substituted and rearranged. Okay. So instead of H, they put CPT, then Cp they have taken to the denominator. That is, they divided everything with the Cp. Then instead of Cp, they substituted gamma R divided by gamma minus 1. Then this gamma R T infinity is A square. Okay, like that they simplified. So this is the another form of energy equation. Now we are applying the linearized theory. So this P is U square plus V square, and U is V infinity plus U cap. This V is V cap. That's what they written here. Instead of this V, they written U square plus V square, then the same term. I simplify within that, I cancel the constant term. That is, so here also I have V square, here also I have V square. I cancel this, you know how to expand it, right? A plus B whole square. Expand and cancel V infinity. You will get this term. Then V infinity, take it outside. I will get V square by A square, which is M square, and remaining ratios. Now I am applying that small perturbation assumptions. So perturbation velocities are very small. then this u by v infinity is small. Then compared to this u by v infinity, u cap by v infinity, the square terms are further small. So I'm cancelling this u cap by v infinity square terms first. Only this term is there. Substitute in the p by p infinity. Okay. Again, this also I have to simplify because in the final equation there is no m term, only u terms are there. So to simplify, we are using binomial expansion. So this is 1, this is, that is 1 minus x, the complete term is x power n. Okay, 1 minus x whole power n, like that the formula is there. So if you apply the binomial equation, this one you will get it. I am cancelling the higher order term. So finally you will get this. Okay, so 1 minus x whole power n, similar to the binomial expansion, we can expand, and I am cancelling the higher order terms. So this is the term you will get it finally, p by p infinity, and rearrange, that is this term get cancelled, like that if you rearrange you will get this final term p by p infinity. Now this can be substituted in the general Cp formula, but Cp formula is 2 divided by gamma m square p by p infinity minus 1. 2 divided by gamma m square p by p infinity minus 1. Okay. So instead of this p by p infinity, substitute this, then cancel. Actually, this is gamma. Cancel gamma m square. Even 2 also get cancelled. This 1 get cancelled. So finally, we are getting this term. Cp is equal to minus 2 u cap divided by v infinity. This is for linearized pressure coefficient for compressible flow. Now we are going to relate Cp for compressible and incompressible. So already incompressible Cp formula derived in the AD1 itself. Okay. So now here I am going to tell, by adding this correction factor, we can include compressibility effect in this incompressible formula. So now I have to compare Cp of compressible and incompressible. So Cp compressible I derived. Actually, similarly, they are writing Cp incompressible. So compressible I will take Cpc. Incompressible I will take Cpic. Okay, incompressible. So minus 2 u cap already given. So here they are taking u bar divided by v infinity. Okay, this is for compressible. In similar way, they are writing for incompressible, minus 2 u bar divided by v infinity. So okay, we'll go to the derivation first. So here compressibility correction we are going to apply in the subsonic. So we are comparing compressible and incompressible flow. So this is the velocity potential equation for compressible flow. Just now we derived linear form, and for incompressible it is Laplace equation, 5xs plus 5y is equal to 0. This is for incompressible. So we have to compare these two phi equations, but already x term is here. So if I use the same x term here, it will be confusing. So instead of x, here they are using zeta eta. Okay, so this is for incompressible. Instead of 5xs 5yy, just to differentiate, here they are using 5 bar. Instead of xy, they are using zeta eta. So in the compressible, so instead of this term, they are taking b square. Simply they are assuming. Later they will substitute this term only. For simplification, they are taking b square because Mach number will not vary. If you take one problem, definitely free stream will be constant. So this is the constant term. So instead of this, they are taking b square. So this is for compressible flow. Now this is for incompressible flow. Both are velocity potential equations. Now by comparing, they are finding these three terms. Okay. Few books they mention how to get this term from these two equations, and few books they verified. For example, if you substitute this in the second equation, you will get the first equation. Or if you substitute this in the first equation, you will get the second equation. Like that they are verifying. I think in the Anderson they verified. Okay. So for the verification, they are substituting this term in the second equation. So what I need is 5 cap 5 bar zeta zeta. So I know 5 bar. From that, first I have to find 5 bar zeta, then 5 bar zeta zeta. These two I have to find it. Okay, so first I am finding 5 bar zeta, which is dou 5 bar divided by dou zeta, and instead of 5 bar, I can substitute b 5 cap. B is constant, take it outside, and remaining is dou 5 cap divided by dou x that is 5 cap xx. Okay, so all three terms we have to substitute. So first I am finding 5 bar zeta. So instead of 5 bar, b 5 cap, instead of zeta x, then b is outside, remaining term you will get it. Then 5 bar zeta means dou squared 5 by dou zeta square. Same procedure. These two we have to replace, you will get this term. Similarly, you can do it for eta also. Now substitute in the second equation, you will get the first equation. This is the verification procedure. So once we verified, so this is our final comparison. Now I know CPC formula, CP incompressible formula, where U cap is dou phi by dou x, U bar is dou phi bar by dou zeta. Again, I am taking this U cap, instead of phi cap, it is phi bar by B, instead of x, it is zeta. Okay, B is taken outside. Then this is equal to U bar. Okay, so U bar by B. So what I am getting is, instead of U cap, I am getting U bar by B. So B is nothing but root of 1 minus m square. So this is the general CP compressible formula. Instead of U bar, I am substituting, instead of U cap, I am substituting U bar by B. So then again, instead of B, I am substituting 1 minus m square. And this term is CP incompressible. Okay. And similarly, you can write CL-CM equation also. Okay. CLC is equal to CL incompressible divided by root of 1 minus m squared. Again, old method. Further, it got improved by Carman, Sian, and Lighton. They also further modified this equation. And here they compared with the experimental value. So these dots are the experimental values, CP formula. So if you use Prandtl-Glatt, see the line is just below the experimental value. It is not matching. Prandtl-Glatt compressibility correction, it is little bit closer with the experiment, and further it is modified by the Carman. So now it is many points almost it is matching. Then Leighton further he modified. So now these points are maybe little bit closer to that.